Hello, everybody. Again, hope everybody's doing well today. You can see me, I'm still at home here, and that's my pet goldfish behind us. They told me he would only get like 3 inches in length. He's got a little bigger than that, but fortunately, we have a really big tank. So let's get started. I know you're tired of hearing this drivel. We'll talk about Chapter 11, atmosphere testing on a site. And this is a pretty short chapter. That's why chapter 11 and 12 are together. And I'm going to sneeze, I think. Yes, I am. Sorry about that. Anyhow, chapter 11, atmosphere testing. How to determine the condition of the atmosphere. When you're on a site, don't know what the heck's going on, not a good place to be in. You need to know. Chapter objectives: understand the different methods of identifying hazardous chemicals in the atmosphere, explain different air monitoring technologies, and apply various field test methods. Air monitoring is the use of direct reading instruments to produce instantaneous data, while air sampling is use of a sampling pump and collection media that produces samples for laboratory testing. At OK Foods, we used to have a Draeger pump, and that we had a couple of them, and they were a little bit of a pain, because you had to have these capsules with them for different types of gases, and they didn't last very long in storage. So you could buy $100 worth of these things, and then 6 months later when you need them, they're all out of date. So that was kind of a pain in the butt. And also, they're going to just test right now. So their monitoring, in my opinion, is better. Of course, then you need to have an instrument for each of these chemicals too. Anyhow, for OSHA, air monitoring must be conducted to determine oxygen content, flammability, and ionizing radiation, required for initial site entry and throughout the response. Air monitoring also helps us to determine the PPE we need, defining protection areas, assessing potential health exposure risks, and the need for specific medical monitoring. Because remember, it's not just what the toxin is or the hazard is, it's how much of it. The concentration of it is an important factor as well. When selecting air monitoring equipment, some criteria should be used. Good idea. Simplicity of operation. Yeah, I'm all in favor of that. Reliability, of course. Portability. It wouldn't be much good if it wasn't. Environmental conditions it'll be used in. Storage and transport requirements. Selective and sensitive. And is it intrinsically safe? Don't know how they determine that, but that's one of the criteria. It's a good idea to use. Air monitors utilize different technologies to detect different threats. Photoionization devices, electrochemical sensors, catalytic bead, we just use a Wheatstone bridge, which is a type of electrical setup. Colorimetrics, radiation detectors. Photoionization detectors, or PIDs, are used to detect volatile organic compounds, VOCs. They use an ultraviolet light to cause ionization of molecules. Ions can be measured in parts per million or parts per billion. Must use correction factors for accurate concentrations. So the gas enters the instrument, and an optical system uses an ultraviolet lamp to break down the vapors and gases for measurement. It passes by the UV lamp. It's now ionized. So charged gas ions flow to charged plates in the sensor, and current is produced, and then the current's measured, and the concentration is displayed on the meter. And then these gas ions get put back in, it reforms and exits the instrument intact. Pretty slick. Electrochemical sensors are chemical specific. They use an electrolyte solution, solid or gel, to ionize chemical vapors. The ions flow to electrodes, producing a current. There's the ions again. Readings are usually parts per million or percent. And that's how it does it there. Catalytic bead is used for LEL sensors. 2 beads are heated to a set temperature. A reference bead is shielded for comparison. An active bead contains a catalyst coating. As flammable gas reacts with a catalyst, a resistance is produced and measured. This resistance is measured on a Wheatstone bridge circuit, and the percent of LEL volume reading is produced. Catalytic bead LEL sensors must be used in conjunction with an O2 sensor. With low oxygen content, readings may be inaccurate. Must use correction factors for accurate concentrations. Colorimetrics uses materials coated with a reagent. These reagents are designed to react with specific chemicals. The reaction produces a predicted color change. Radiation detectors, numerous radiation detectors exist, like Geiger-Müller or dosimeters. Most are designed to detect ions or electrons and amplify the current. They produce readings in CPM or RPR, R per hour, which is probably Rankins, can detect alpha, beta, or gamma X-rays. When I worked in nuclear weapons, of course, have radioactive, and they're pretty well sealed up, though. We had to wear these little plastic black dosimeters just to wear them on your belt, that old keychain on them. We wore them, but nobody ever tested them. So I don't know. After a while, we just didn't wear them anymore. Geiger-Müller probe, that's how they work. Anode and cathode, filled with gas, quench gas. I'm pretty sure it's a pretty simplified design. Doesn't really explain how to work, but again, it gives you an idea. Air monitoring techniques. Effective air monitoring is dependent upon technique and operator knowledge. Understanding chemical attributes can help you determine how you monitor and what you use, such as the vapor density, the specific gravity, pH, volatility, and unknowns. So if you know what you're dealing with, if you know that the specific gravity is of something, or the vapor density is pretty low, it's going to waft up in the air. If it's high, it's going to be down. Specific gravity, you know, it's going to float in water or sink in water. So these are things you need to know. You must monitor all areas of an incident from floor to ceiling. When walking, use a slow pace to ensure the vapors can be properly measured. Allow time for the chemical to flow through the sample tube to monitor, typically 1 second per 1 foot. So every foot will move at about a second. So it has to be slow enough for the meter to read it. If you go too fast, you might get ahead of yourself and you'll be into a reading that's too high when you don't want to be. Golden rule for monitoring unknowns is radiation first, and then pH, oxygen, LEL, and chemical specifics. In confined spaces, chemicals gather in layers or in certain areas. Responders should slowly monitor in sections to allow for adequate chemical detection. Confined spaces are places that you have to be extra vigilant in everything, just because of the nature of the beast. This is a very basic air monitoring technique. The first stage, the top, the third stage, the middle, and fourth stage, the bottom. And remember, continuous monitoring is a must. You got to keep monitoring, be sure everything's good. So that's it. Again, read the book, and I gotta go. I gotta feed my goldfish. I don't know. Maybe I'll have sushi tonight. Bye.